Good morning, this is Christina Long and this is the Science 411. Today's video is over solutions dealing with terms and processes. It's not too much. The vocabulary piece is probably pretty large and it's probably new to most of you, so make sure that you follow along. So, what is a solution? So some terms that you need to know: solvent and solute. So a solute is the substance that gets dissolved, and the solvent does the dissolving. So in the picture you've got salt there, and then it's going into probably water. I would say it would be water. Water is going to be called the universal solvent, and it's going to dissolve almost anything given enough time. But the solute, again, is going to be the thing that gets dissolved, and the solvent does the dissolving. Now there's an old picture that's used a lot of times, and it's this. So the V for the glass stands for solvent, and the U stands for solute. So the U is solute, like ice cubes in a glass, and that gets dissolved. And so ice cubes are going to melt. So the solute gets dissolved, and then the V, which holds the main liquid, that's going to stand for your solvent, and that does the dissolving. Okay, you'll see that drawing a lot of different places, but it's an easy way to remember which is which. But those are two terms that you're going to need, and it's very important that you understand that you have to have a solute plus a solvent in order to get a solution. You have to have both. You've got to have both to get that, and you cannot have one without the other. Okay? So, you've got two other terms, soluble and insoluble. And a substance that is soluble can be dissolved, and just like you would use an IN for the beginning of another word, that IN prefix normally means it's negative, and so an insoluble substance cannot be dissolved. Then you've got miscible and immiscible, and these are two upper tier terms. A miscible substance is a liquid that'll dissolve into each other. So from the picture you've got ethanol and water, you've got the solvent and the solute there. They're going to mix together. They're going to dissolve into one another. Immiscible means that it will not. And then you've got the last set of terms, electrolytes and non-electrolytes. Electrolytes are liquids that are capable of conducting electricity. And so when you're looking at the picture, you've got these two electrodes coming down into this solution. And the reason is because the solution has broken into positive and negative ions. And that negative ion there, those are actually electrons. And if there are enough electrons in that solution, then it will be able to complete that circuit and the light will get turned on. All right. So, what is a solution? Well, you've got types of solutions here. You've got a gaseous solution, liquid solution. All right, we'll go back for a little bit. Gaseous solutions are air and other mixtures of gases. And air that you breathe is not, if you notice, there is no element called air. So you've got oxygen and nitrogen and hydrogen and helium and all these different gases floating around, but they're a gaseous mixture, which is going to be a solution. And then you've got a liquid solution, and in some cases water's the solvent, and when that happens, it's called an aqueous solution. That's how you pronounce that. It's aqueous solution. That means that the solvent for that liquid solution is going to be water. And again, water is called the universal solvent because it's going to dissolve almost anything given enough time. And then you have a solid solution. And these are combinations of solids, some homogeneous mixtures of metals. They're called alloys. And alloys, the term that you use, like in the picture, you've got this filling there for somebody's tooth. It's a mixture of metal solids. So alloy is going to be used for metal solids. Making a solution. Well, you've got to have the solute and solvent particles are separated, and then then the solvent particles are attracted to the solute. It's called solvation, not salvation, but solvation. And that's when the solvent water, this is called hydration. So dissolving, now you've got two new terms. It's not just dissolving something and creating a solution. It's called solvation, and notice that the solvent is attracted to the solute, which ties into the term solvation. And when the solvent is water, it's called hydration. So, number 3, that's a big thing. Like dissolves like. And when we talk about like dissolves like, this is a huge rule. Like dissolves like. And so you have polar and nonpolar molecules. Okay? And just like you have a north pole and a south pole, you're going to have positive and negative ends to compounds. And nonpolar, it's not going to have either of those. So as an example, let's show you this. Sorry, it's taken a little bit. There we go. Okay. So you've got a polar molecule and a nonpolar. Let's do an example of water. Water is the most common example of a polar molecule. And I tend to look at it as Lewis dot diagrams. So when I'm looking at the Lewis dot diagram of water, when I've got my dots there, and I've got my oxygen and I've got my hydrogen, and when I look at the periodic table, the charge on oxygen is a -2, and then each of my hydrogens are a +1. So if I take my overall charges of -2 and add them to my basically +1 and +1, my overall charge is 0, which is perfect. That's exactly what I want. But when I'm looking at the molecule, it's easy to draw an imaginary line that splits that molecule. And because I can draw an imaginary line that splits it, so I have a negative side and then I've got a positive side. And because I've got those two, that means that I have a negative pole and a positive pole, which means I'm dealing with a polar molecule. A nonpolar molecule, let's look at, say, CH4 or methane. So I have C, which I've got 4 of my valence electrons, and then I've got my 4 hydrogens. Carbon tetrahydride, or otherwise known as methane. So I've got my Lewis dot diagram there, and then I start assigning charges. My hydrogen in each case is going to have a +1 because it's going to give away an electron in each case to the carbon. And because of that, that's going to give carbon a big fat -4 charge. And now I've got a negative basically surrounded by a ring of positive. So let me show you that again. I've got a negative center surrounded by a positive ring. There is no pole there. You've got different charges, yes, and overall the charge is still 0, which is what you want. But there's no positive end and there's no negative end. Therefore, you're dealing with a nonpolar molecule. Now sometimes it's easier said than done to draw those pictures. And so there are certain rules that you can remember. as far as what's a polar and what's a nonpolar, and that'll be on the next thing. But like dissolves like. Polar dissolves polar, and nonpolar dissolves nonpolar. You guys have heard that oil and water don't mix. Well, the reason that they don't mix, it's not just a figurative statement, it's a literal statement as well, because oil is polar. All oil-based molecules are polar, or nonpolar, I'm sorry. And then water is polar. So if it's a water-based molecule, it's polar. Water-based is going to dissolve water-based. And then oil-based is going to dissolve oil-based. But you can't take water and dissolve an oil-based molecule. I mean, you can over time, but it's a long, long time. So if you're going to paint your room over this extended time out, and you use an oil-based paint, and you go to wash out the paintbrush, excuse me, and you're using water, well, you're going to be sitting there a long time, and you're going to make a huge mess. But instead, if you use paint thinner or gasoline even, which is an oil-based molecule, it'll dissolve that paint really well and it'll take it out. So, like dissolves like. That's something that you need to remember forever. So, polar and nonpolar. This is an easy chart to kind of remember. Polar is going to be water, methanol, ethanol, acetic acid, acetone. Ionic compounds. Now, it's not just going to be acetic acid. You're going to look at strong acids and strong bases are going to be polar. But ionic compounds are going to break apart when you put them in water and they're going to make ions. Nonpolar are going to be things like carbon tetrachloride, and we just did carbon tetrahydride. Toluene, which is going to be a paint thinner. Hexane, heptane, octane, benzene, oil. Any oil-based molecule, and in general, molecular compounds are going to be nonpolar molecules. So dissolving an ionic compound in water, and this is just something to kind of pay attention to. Water is polar because it has two oppositely charged ends. So as you can see, that red dot signifies oxygen, and that's your negative side. And then you've got your two positive ends with your white dots for your hydrogen. So overall, it's a zero charge, but you've got a positive and a negative end. So the positive end of water is attracted to the anion of a different part of the water. So here's what ends up happening. Let's say that you've got, there's your water, okay, and you've got this negative charge out here. Well, for the solute, it's going to be attracted to the positive end of the solute, the negative and the positive, because opposites attract, okay, and it'll start breaking down that solute. It'll be pulling it apart piece by piece. So the combined pull of water molecules overcomes the attractive forces of the solute. So notice that the water it's getting close to the solute and it's just picking it off piece by piece. The ionic compound is dissociated into individual ions. Now, dissociated, that's a fancy term for broken apart. All right. Another term for that is ionize. So, dissociate means ionize. And broken apart. Both of them. So, with chemistry, I've told you several times, if you can do things with one word, that's no fun. They're going to add different words to it. So, that's what they've done there. So, you've got sodium chloride, and it breaks into a positive sodium ion and a chlorine negative ion. How do you know if it's positive or negative? Look at your chart. All right, so dissolving molecular compounds in water. Water's charged ends are attracted to charged portions of the solute. The solute surrounded by water molecules, and the solute remains intact. Now, to speed up the rate of solvation, again, the term solvation means to dissolve or to break up or disassociate things. So how do you speed that up? You can stir or shake something, and that's called agitation. You can break apart the solute, so you can break it into tiny pieces. You can heat it up. Those are 3 ways to do it, and let me give you, again, that term agitation is the fancy term for stir or shake, okay? And breaking apart the solute, basically you're increasing the surface area. So if I give you something and ask you to dissolve it, you've got a couple of choices. If you're looking at this as which one is going to dissolve the fastest, again, you can only dissolve from the outside in. So you've got surface area there, and then you've increased your surface area, and then you've really increased your surface area. Okay? So by doing that, by breaking up the solid into smaller pieces, you give it more area for the solvent to attack, and it speeds up the process of solvation. Alright, now you've got a solubility curve there, and understand that you're going to be asked some questions on how to read these. So when you're looking at this stuff, you have to pay particular attention to a few things. Number 1, the grams is your dependent variable, and it's going to be on that y-axis, and then you've got temperature down here, and the temperature is pretty important. In general, as you heat things up, the solubility increases. Well, where does that happen? Well, it happens there, and there, and there, and there, and there. And even to a slight process right there. Okay. So for all of those compounds, whatever they are, as you heat them up, it will dissolve more and more of that solute the more you heat up the solvent. But notice that you've got some lines that go down. And I will tell you that with those, you've got 3 on this diagram. In general, solids and liquids will increase solubility, and that's how much something is dissolved, with an increase in temperature. In general. Not always, but most of the time. And that was the red lines. But the opposite is the case for gases. Gases are less soluble in higher temperatures. Now, here's the thing. That should make sense. Because if you take a soda, and I'm sure most of you are drinking sodas right now, but if you take a soda and it's cold, originally, when you first open it, it's going to have a lot of carbonation and it's going to taste good. The longer you go throughout the day, and let's say you just sip on it kind of like I do, the longer you go throughout the day, the less carbonation it's going to have. And it's not because it, quote, wears out, it's because the liquid gets warmer, and the warmer the liquid gets, the more energy the gas gets, and then the gas leaves that liquid. It's less soluble when it's warm. So if you're trying to keep the most carbonation in your soda, you keep it as cold as you can. Okay, but those downward curves are going to show you most of the time gases. Alright, so you've got some concentration terms. Concentrated It's a solvent that has a lot of solvent or solute per solution. Then you've got dilute, and that's got a lot of solvent. That means you've got more stuff that you can get dissolved. And then you've got saturated, and that's a saturated solution is one with the maximum amount of solute it can have. And then you've got supersaturated, and that's a solution with more solute than it can hold. All right. So I pulled up a page from Honors Chemistry as Solution Terminology Review, and this should give you a little bit better view of what unsaturated, saturated, and supersaturated actually is dealing with. So down at the bottom, you've got your solute added to your solvent. In most cases it's water. And then together it's going to make a solution. And all of these are dealing with types of solution. So you can't get to a solution without a solute and a solvent. But now we're looking at classifying those solutions once you have them. Are they unsaturated? Are they saturated? So, over on the left, you've got unsaturated. It's got more solute dissolves. That means that when you put a solute in the solvent, it's going to dissolve immediately. So, saturated solution, that means it's got all it can hold. It can't dissolve any more solute. And then a supersaturated means that it's got actually more than it can hold, and it starts to add or grow crystals because that extra solute is looking for something to bond to, and it bonds to itself. Another way to look at it is over on the right. Again, you drop the solute in and it dissolves. In the middle for saturated, it's going to sit at the bottom. You can't dissolve anymore. And then with a supersaturated, it's going to start growing. And that's kind of how they make rock candy. But it's kind of cool. Anyway, that's again another way to look at your solubility or solution terminology. It's important that you go through and that you make sure that you know all the terms for this unit. I hope you guys are staying well and keeping safe. Know that I miss you. And until next time, have a good one.